So we'll continue on Pauli matrices. So from last lecture, we introduced the Pauli matrices, right? It's very easy. It has three. Sigma x, I call it sigma 1, right? Off diagonal, 1, 1. It has sigma y, which I call it sigma 2. This is not z, this is 2. It's negative I. The way I memorize it, I learned from someone, is that negative is light, smaller, right? So it floats on the top. So you think of a way to memorize it, right? It's also off diagonal, and it is I. And sigma z, which is 1 minus 1, right? And Pauli matrices has these properties. First, they are Hermitian. This is a concept you must be very familiar with now, right? It means that its adjoint equals to itself. So what is this dagger? How do you operate? Transpose and followed by complex conjugate of the elements, right? You need to be very familiar with this, okay? And then they actually, if you multiply to itself, is an identity matrix. Sigma x equal to I, sigma y equal to I, sigma z equal to I. They are traceless. The trace means sum over the diagonal of the matrix. If you sum them over, for example, the trace of sigma z is 1 plus negative 1, so the sum is 0. So they are all traceless. And you will find that this is a very useful property for us to prove some identity later, right? And we also claim that, which we'll say in the next line again from last lecture, all the Hermitian matrix, any Hermitian matrix, okay, 2 by 2 Hermitian matrix, can be expressed as a linear combination of these Pauli matrices and also the identity matrix. So basically we say, okay, now I call I equal to sigma 0, right? And I have sigma 1, sigma 2, sigma 3. So that has 4 degrees of freedom. They become the basis of another space. Again, this space is something we cannot feel. It's an abstract space, right? But it is a linear vector space as we defined in our second lecture. And linear vector space obey a few properties, right? You can go back and check, but they obey it. So do not feel very uncomfortable when you see that the bases are matrices, okay? So any 2 by 2 matrices, Hermitian matrices, I should say, can be written as a linear combination of them. Just like you know that any vector, right, in the 3D space, any vector, you give me a vector, it is a linear combination of A0 x hat plus B0 y hat plus C0 c hat. So any vector in this room can be represent a linear combination of A x hat, y hat, c hat. This is the space we live in. We are very familiar with this. So please accept the fact that maybe there's another space. Of course, this is an abstract space. Any 2 by 2 matrices, it is a vector now in this sense, okay? But it's not a vector in a column, right? It's a matrices. It's a vector in the abstract sense. If you don't want to call it vector, fine. But just say that this can be expressed as a linear combination of this. Can you see that? Right? Sigma 0, sigma 1, sigma 2, sigma 3 are just x hat, y hat, z hat. I mean, correspond to that. And then you can have a real number in front of it. And in this particular case, indeed, A0 dash, A1 dash, all the way to A3 dash are real numbers. They need to be real numbers. Okay? And because of that, I can write it in this form. I can also write it as this. I just call it A0 dash I, which is I is just sigma 0, right? But this one is what? This one is no difference, nothing special, but just the inner product between this vector. This is a real vector. A1 dash, A2 dash, A3 dash. And this particular vector, this again is another vector, very strange, right? Instead of having real number as the coefficient, it has sigma x, sigma y, sigma z as the coefficient, right? So originally I should write it as, if it's a vector, I will write it as A0, like here, right? We used to write this as A0 B0, C0. That's how we write it. And we say we have A0 part of X hat, B0 part of Y hat, C0 part of Z hat. Same here. I have sigma X part of X hat, although this sigma X is a matrix. Okay? So this one is just this Pauli vector inner product with this real vector. Just a definition. Any questions? And we are going to use Pauli vector very soon, which is very important. Okay, so basically you should understand everything, except that it's very confusing if you have not seen that before. So you need to accept it, keep thinking about how it is related to there, and accept the fact that the coefficient doesn't need to be a real number, it can be a matrix. Or in this space, the basis doesn't need to be a vector, it can be a matrix. Okay, so that's what we learned last time at the end. Right? So let's continue to understand the Pauli matrix more. The first thing we want to learn is the commutation relationship. You might not be familiar with this, but we need to learn it right away. So for Pauli matrix, right, if you look at this commutation relationship, what does it mean? It has a definition for commutator. If I write this square bracket, I say sigma n, sigma m, comma, sigma m, right, square bracket. It means this is a commutator, which is defined as sigma n, sigma m, multiplication, minus sigma m, sigma n. Now, in our regular algebra, when you see this, what would be the answer? 5 times 3 minus 3 times 5, 0. We say they commute, right? Whether you put it in front or after, it doesn't matter. But these are matrices, so they don't commute in general. Usually they don't commute. Okay? Then what is the answer? It is equals to summation L 2I epsilon n m L sigma L. So there are so many things we need to learn if you have not learned that before. First of all, commutator. So please just take it for granted, memorize it. A sigma n times sigma m minus sigma m times sigma n. Okay, that is the definition. Nothing to argue about. Definition, accept it or not. Okay, and then we have this complicated form. So let's learn this one by one. First of all, what is epsilon n m L? This is not difficult if we just cool down, right? This is called Levi-Civita, I don't know how to pronounce actually, symbol. So what does it mean? So you can think in this way. There are many definitions. Of course, they are very complicated definitions, but just think in this way. If I put the index 1, 2, 3. Remember, I did not say that was n and m, right? What are n and m, by the way? Sigma n, sigma m. What do I mean when I put sigma n? Yeah, it means it can be any one from the Pauli matrices, right? So here it means that what I'm saying here is n, m, l. These just symbols, right? Variable. They are either 1, 2, or 3, or x, y, z, right? So just any of the Pauli matrices. That's it. So first of all, NML are 3 indices, right? You can be anything because n can be 1, 2, 3, m can be 1, 2, 3. So just given that this is one way to learn it, right? This is not a formal definition, but it's equivalent. Sigma 1, 2, 3 equal to 1. Okay? If you're sigma 1, 2, 3, then it is 1. Now, if you swap the symbol, right? If I swap the symbols for even number of time. For example, sigma 2, 1, 3. What did I do from here to here? just swap 1 and 2. Right? It becomes 2, 1, 3. So sorry, let me start with odd number, so that will be easier. Odd number. Right? Do you get this? When I say swap for odd number of time, I just pick any of them, I swap them. I get something. That something is 2, 2, 1, 3, right? Then it is negative 1. Okay? If I swap it for even number of times, for example, I further swap 2 and 3. It becomes 3, 1, 2. Right? So, in order to get one from 1, 2, 3 to 3, 1, 2, how do I get it? I can first swap 2 and 1 becomes 2, 1, 3. And then swap 3 and 2 become 3, 1, 2. Do you see that? Then it will become 1 again. It's just a definition, right? But if there is a repetition of the symbol, for example, epsilon 2, 2, 3, then it would be 0. Is that okay? Now, another way to look at this is like that. You can also think of 1, 2, 3 as clockwise. If your symbol is like 1, 2, 3, 3, 1, 2, 2, 3, 1, then they are plus 1. But if it's opposite, the symbol becomes 1, 3, 2, 3, 2, 1, 2, 1, 3, 2, 1, 3, then it's negative 1. That's another way to memorize if you want. Okay? So here is very troublesome. Then let's look at this again. We can really look at this and do it carefully. For example, what is the summation L2I epsilon NML sigma L? What does it mean? This is a good practice. Let's do this step by step. It means, maybe I better make this clear. When we do the summation, it means go from 1 to 3. So first, L equal to 1, I have 2I epsilon NM1 sigma 1 plus 2I now NM2 sigma 2 plus 2I sigma NM3 sigma 3. Do you see what I'm doing? You should be very familiar with this already, but in case you don't, I try to spell it out. When you say summation L of this one, no worry, just copy everything, except that you keep changing L according to the index and add them together. So I change L first, L equal to 1. I put 1, add, and then L equal to 2. And then add L equal to 3, and add them. Right? Now, so you see that this one go through 1, 2, 3. Then it means that this term, 2 of terms must be gone. Right? Because NML must be 1, 2, 3, right? Must be, right? If M and L, one of them must be 1. If it is, N may be equal to N may be equal to M. Right? So if N equal to M, what is the result? Can someone tell me based on what we just learned? If N equal to M, 0, all of them are 0. Because n equal to m, we say if there's repetition, then all these terms are 0. Make sense? Okay, good. This is 1. But it's possible that n not equal to m. If n is not equal to m, then if n is not equal to m, then they occupy two indices already, either 1, 2, 1, 3, or 2, 3, right? Because they are not the same. And then here I have 1, 2, 3. So only one of them will be non-zero because you occupy two numbers. So either 1, 2, 1, 3, or 2, 3. So two of the term will be 0. Right? For example, if n is 1, m is 2, then this is 1, 2, 1, right? 1, repeat, right? And then m is 2, repeat. So both of them are 0. Only this 1, 2, 3 is left over. Right? Do you get it? You can try. Right? This is easy. You just try to plug in example, then you will get it. So if that is the case, this is just equal to 2I epsilon n ml sigma L with L not equal to mn. Right? So sometimes if you read the textbook or even Wikipedia, they just put this one equals to the term like this and claim that L not equal to mn. Right? So how about this? If this is too much for you, I request you to only memorize this. How do I write it? This is just your 2I epsilon n ml sigma L with L not equal to mn. This is the answer. You can think in that way, right? But more formal way is that you need to sum over L, but two of them will be 0. Okay, so they make sure that, let me give an example. Let's give an example that will be the best. Okay. But any questions? For some of you, it's easy, but we do need to do some exercise. For example, what is sigma x, sigma y? Then let's go back, right? Maybe you can evaluate already, but if you want to go back to index 1, 2, 3, this is sigma 1, sigma 2. And what is the definition of commutator again? Remember, we just try to say AB minus BA, that's it. 3 times 5 minus 5 times 3. That's what we're doing. That's very simple, right? Sigma 1, sigma 2 minus sigma 2, sigma 1. Memorize this. This should be easy. If they commute, then they are the same. If they don't commute, then they are something, right? And as I just said, this equal to 2I epsilon 1, 2, 3, sigma 3. Because now L equal to 3. Right? Let's go back to this equation. 2I sigma NNL, epsilon NML, sigma L, right? 2I sigma NM, here N is what? N equal to 1, M equal to 2, right? From the previous equation. And what is sigma 1, 2, 3? I'm sorry, epsilon 1, 2, 3, I'm sorry. 1, because it's 1, 2, 3. You start with 1, 2, 3. That is 1, right? So this is equal to 2I sigma 3. This is the answer. Okay? Let's check, right? Let's check. Let's check if that is correct, because we also need to learn the basics. Sigma 1, sigma 2 minus sigma 2, sigma 1. What is sigma 1 again in matrix form? It's sigma x, right? 0, 1, 1, 0. What is sigma 2? Anyone can memorize? 0 minus I 0. Very good. And then we do the subtraction. You see, they are not necessarily the same because now it's 0 minus I 0 times 0, 1, 1, 0. Right? So let's do the math, right? The first one, I hope that this is easy for you. 0, 1 times 0 I give you 0 times 0 plus 1 times I, right? So this is I. Second one is 0, 0, negative I. I'm talking about this one. 0, 1 times 0 I becomes I. 0, 1 times negative I 0 becomes 0. 1, 0 times 0 I becomes 0. 1, 0 times negative I becomes negative I. Okay, so I do the same thing for the next term. It's negative I. How about the next one? Anyone know how to do it? 0. How about the lower left? Also 0. How about lower right? Thank you. So I do the subtraction. This gives me 2i, 0, 0, negative 2i. Factorize it, 2i, 1, 0, 0, negative 1, which is sigma 3, sigma z, right? So I prove that I show that it's consistent with this equation. Now, so in this class, I will require you to be very familiar with bracket and also matrix because that can help you to get many things done. You need to be very familiar with this. Okay? So that is the anti-commutation property. Now, no one will ask you to memorize it. You put in your cheat sheet for exam or whatever, which is good, but you should know this. At least you know how to Google, right? How to ask ChatGPT. What is the commutation relationship of Pauli matrices? Then you get this equation for sure. But if you don't have this concept, you don't know anything, right? And it's going to tell you this Levi-Civita symbol also. You understand how to interpret it. Any questions? Yeah. Physical consequence of this commutation relation. If two of the matrix commute, they have the same eigenstate. They can be diagonalized at the same time. Yeah. If they don't commute, they cannot. Then it means that you cannot measure them accurately at the same time, and that's the result of Heisenberg uncertainty principle. So, for example, you can represent the position in a matrix also, right? Which you're probably not familiar yet if you have not taken quantum mechanics. And momentum also as another matrix. They do not commute. And their commutation relationship is xp minus px equal to ih bar. And from there, you can deduce the Heisenberg uncertainty principle. Yeah. So this is the physical consequence. Yeah. 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 So let me talk about the. Actually, I don't know much about the physics meaning of anti-commutation, but I'm going to talk about that. No, this have nothing direct relationship to boson or fermion. It is an operator, right? So we are not talking about boson or fermion at this moment. It's just the operator. It doesn't refer to any particles. That maybe you're talking about symmetric wave function. That is wave function. That's not operator. Right here, we're talking about operator. So the wave function is symmetric. So you do the permutation operator on it. For fermion, I think you get a negative sign. But for boson, you get a plus. Yeah, I'm not very good on that, but again, here is only operator, right?
But you just don't understand. I mean, you just don't.
We now don't have any physics here. We're just talking a general operator property, right? For example, in this Pauli matrices, you have this commutation relationship, and they don't commute. That means you cannot measure x and y eigenvalue at the same time, right? Because this is a good question. If you can follow, just relate back this to observable. we have talked about the measurement. Every measurement is related to an observable, right? And the observable, what you're going to measure is the eigenvalue of that operator. So every measurement is correspond to a matrix, right? And the measurement outcome is the eigenvalue of that matrix. So for measuring the spin in the z direction using a magnetic field, it corresponds to sigma z. But you measure the spin in the x direction when your magnetic field is in the x direction, it corresponds to sigma x. And basically here is saying that you cannot know their eigenstate at the same time because they don't commute. And it also means that you cannot measure the spin in the z direction and the x and the x direction at the same time because they don't commute. So that is the Heisenberg uncertainty principle. This is a case similar to you cannot measure position and momentum accurately at the same time because they don't commute. Okay? Yeah, that's a good question. You see, there are many pieces we need to keep repeating, and finally you will just get used to it and you know what's going on. Okay? So now let's go to the anti-commutation relationship. This is just an equation that we need. And you have commute, and then you also have anti-commutation. And what does it mean? Now you use this curly brace as the symbol, and you put it like sigma n. So this is not only for Pauli matrices. Any matrices you can analyze in this way, right? This is just a definition. Can you guess what would be the equation for anti-commutation? So for commutation is sigma x, sigma n, sigma m minus sigma m, sigma n. How about for anti-commutation? If I say they're very similar, then what will you guess based on the name? It's like anti. Huh? Okay, sigma, okay. That's a good guess. So you mean swap, right? Yeah, but turn out it is not, but that's a good guess because you really cannot guess. There another possibility is use plus, right? Just a name, yeah. So this is the definition. Still, the first term go first, sigma n, sigma m, plus sigma m, sigma n, instead of minus. So what will be the result? This is much easier. It is equals to 2 delta nmi. So we learned about delta nm before, right? This is a conical delta, right? Delta mn equals to 1 if what? We learn it in the orthonormal basis. If n equal to m, right? And then equals to 0 if n not equal to n, right? Just the conical delta. So which is very easy to see, right? For example, if n equal to m equal to, let's say, x, how about x? Then you have sigma x. Oh my God. You have sigma x what is this? Sigma x plus sigma x equals to 2 sigma x. What is sigma x times sigma x? Thank you. Sigma I equal to I, right? That's why I need you to memorize this. This just equals 2I. So that is very natural, right? If n equal to m, we're talking about same matrix, it's just equal to I. But if they are not turn out to be 0, Okay, so this is very important. I'm not going to prove it, right? If n not equal to m, then it means sigma n, sigma m equal to sigma n, sigma m plus sigma m, sigma n equals to 0. Okay, you can prove it, right? But I mean, you can try to prove it, but let's just take it for granted here. It's easy to prove because you just need to go through the combinations. Right? I mean, yeah, that's the way I know. Okay, so we learned two things. One is commutation relationship. One is anti-commutation. First, you need to know what this means. For sure, you need to know, right? If you don't know this, don't tell people you have studied quantum mechanics or quantum computing, right? You need to know. And it's easy to memorize. AB becomes AB minus BA. Here, AB becomes AB plus BA, right? Commutation, anti-commutation. And then for this equation, hopefully you gradually can memorize